In this video, we're going to talk about how we can use the normal distribution to approximate the binomial distribution. So here's the setup. So it says some binomial problems would be quite tedious to do without this allowance of an approximation from the normal distribution. For instance, if we know that 10% of men are bald, what is the probability that fewer than 100 are bald out of a sample of 818? So to solve this binomial distribution, we'd have to do the binom PDF, and you'd have to do it for that 0 men are bald, then 1 man is bald, then 2 men are bald, all the way up to the 100 if we want fewer than 100. So you'd have to add up 101 different numbers. Well, the good news is that the normal distribution can help us approximate it. So there are two conditions that we first need to, well, there's one condition. First, we'd have to have a simple random sample. I'm going to put 0 here. Simple random sample. Then we need to have that n times p is greater than 5. So the number that you're sampling times your probability of success is bigger than 5. And n times q is greater than or equal to 5. Remember that q is always 1 minus p. And then we're also going to have to use a continuity correction here. So based on whether we want to include a number or not, we're going to go down by 0.5 or up by 0.5. And this is just because we're using a continuous distribution to approximate something that's discrete. So first, we'll verify that the conditions are met. Then remember, with the normal distribution, we need a mean and a standard deviation. So we use the mean and the standard deviation from the binomial distribution. So remember, the mean is just n times p, and the standard deviation is the square root of n times p times q. Then you're going to identify x, and by this we really mean find your boundaries, your lower limit and your upper limit, and we'll need to use the continuity correction. Okay, so for this problem up here about bald men, a p is the probability that a man is bald, and we were told that it was 10%. So as a decimal, that's 0.10. Q would be the probability that a man is not bald, which we'd do 1 minus 0.10, and we'd get 0.90. And our n is the total number we're sampling, 818. So n times p will be 0.1 times 818, which will give us 81.8. And n times q would be 818 times 0.9. Which we see is 736.2. So both of those are bigger than 5, so we're okay. So next we're going to find the mean. So n times p, which we actually just did up here. So 81.8. And our standard deviation will be n times p, the square root of n times p times q. So 818 times 0.1 times 0.9. So we get 8.58. Now we want fewer than 100 being bald. So fewer than 100. Now that means we don't want to include 100. We want it to be less than 100. So if we think of a number line, and we have 100 on here, and we want less than, and we don't want to include that. So we're going to go down by just 0.5, so 99.5. So our lower, and that's what we're going to use as our interval. So we'll go from negative 1,000 up to 99.5. So negative 1,000, 99.5. We'll put our mean in, 81.8, and then our standard deviation, 8.58. So what did I put in there? So 0.9804 would be our probability. Okay, so we're going to look at two more examples. So one here with many parts so you can see how we're actually going to make the intervals. So here we know that, it says, we know that 32% of all COTC students are under the age of 21. We take a random sample of 50 students. So our N is 50. Our probability that a student is under 21 is 32%. So our probability that someone's not under 21 would be 68% if you do 1 minus 0.32. So next we're going to want to find our mean and our standard deviation. So remember the mean is N times P. So 50 times 0.32. So 16. And our standard deviation is the square root of N times P times Q. So the square root of 50 times 0.32 times 0.68. So if we rounded 2 decimal places, the 8 would bump the 9 up to a 0, so it'd be 3.30. Okay, so part A says, what's the probability that exactly 30 out of the students are under 21? Now, normally, you remember when we said continuous exactly would be 0, but this is actually coming from a discrete distribution where you can have exactly a number. So if we think on a number line, we want exactly 30. Well, that's what we want. Well, we're actually going to go down by 0.5, so 29.5, and go up by 0.5, so 30.5, and that's going to be our interval. So we're going to do normal CDF of 29.5 up to 30.5, comma the mean, which was 16, comma the standard deviation. So 29.5 to 30.5. So this is giving us scientific notation. So notice that we have this e to the negative 5. So that means we're going to move the decimal 5 places to the left. And it's going to give us 0.00002 if we round. Okay, so really small chance that exactly 30 students are under 21. So part B says, what's the probability that at least 30 students? So there we would mean 30 or more. So 30 or more. Now we do want to include 30 here, so we're actually going to go 0.5 in the opposite direction. We're going to go down to 29.5 to include 30. So our interval will go from 29.5 up to 1,000, and then we'll keep the same mean and standard deviation. So again, this is scientific notation. Here we're going to have 0.00002. Okay, so part C says, what's the probability that more than 30? Now, more than 30 means we don't want to include 30. So if we have 30 here, we still want to be more, but we don't want to include 30. We're going to start at 0.5 above that, 30.5. So we'll do normal CDF of 30.5 up to 1,000, the mean and the standard deviation. So here, oops, I put 20.5 instead of 30.5. So let's check that. Let's change it. Again, scientific notation, we're going to move the decimal point 6 places. So 0.0000006. So D says, what's the probability that at most 30 students? So we'd be okay with 30, but that's the biggest we would want. So we're going to want everything below it. Now, since we're okay with 30, we're going to go 0.5 in the opposite direction. So 30.5 will be our upper limit. So we're going to do normal CDF, negative 1,000 up to 30.5. Still the same mean and standard deviation. So here we get, if we round to, well, if we round to 4 decimal places, it would round up to 1. But if we put 5 decimal places, we'll see that we have 5 nines, 0.99999. So this says, what's the probability that fewer than 30 students? So this is still less than 30. But this time, fewer than 30 means we don't want to include 30. 30 wouldn't be allowed there. So we're going to have to go down by 0.5. So we'll be doing everything up to 29.5. So we'll have normal CDF, negative 1,000 up to 29.5. And then still the same mean and standard deviation. Oops, what did I do? So here again, we'd have 0.99998. Okay, this last problem says, assume that 42% of us have group O blood. A hospital needs at least 152 donors of group O blood. If 390 volunteers donate blood, estimate the probability that the number with group O blood will be at least 152. Is this pool of donors likely significant? Okay, so our N here, how many donors we have is 390, and our probability of having group O blood is 0.42. So we can find our mean by doing 390 times 0.42, which if you do that gives you 163.8. Our standard deviation will be the square root of 390 times 0.42. Q would be 1 minus 0.42, which would be 0.58. So this will give you 9.75. Now, at least 152 means we'd want to include 152. So we would, and we'd want to go up to 1,000. So since we want to include 152, we're going to go down by 0.5. So 151.5 up to 1,000, the mean and the standard deviation. Now I'm running out of time on this video, so if you put this into your calculator, what you're going to get is 0.896. So is this sufficient? Probably. An 89% chance is pretty good, but you can't be 100% sure that you'd have that many.